Hi everyone, I am Kier and I am thrilled you to have her today. If you are passionate about making mathematics easy and enjoyable, you've come to the right place. On this channel, we dive deep into various math topics, breaking them down step by step so you can master them with confidence. Today, we're going to explore the fascinating world of trigonometry, specifically the Pythagorean identities. These identities are fundamental tools that will not only enhance your understanding of trigonometry, but also equip you with powerful problem-solving skills. We will derive two important trigonometric formulas and see how they apply to real-world scenarios. Let's get started.
The Pythagorean identities are foundational in trigonometry. They originate from the Pythagorean theorem applied to the unit circle. Let's derive two main Pythagorean identities. Let's draw a unit circle first. Consider a point on the unit circle which has a radius of 1. The coordinates of any point on the unit circle can be represented as cosine theta and sine theta. The Pythagorean theorem states that in a right triangle, the square of the hypotenuse equals the sum of the squares of the other two sides. The hypotenuse is C. The legs of the triangle are cosine theta and sine theta. This is a unit circle, a circle with a radius of 1 centered at the origin on the coordinate plane. Substituting A is equal to cosine theta, B is equal to sine theta, and C is equal to 1, we get cos theta squared plus sine theta squared is equal to 1. And now, let's simplify. And there you have it, the first Pythagorean identity. It is fundamental and forms the basis of many other trigonometric identities. And take note that any point on the unit circle can be described by coordinates x and y. For trigonometric purposes, these coordinates are defined as cosine theta and sine theta. Drawing a line from the origin to the point, cosine theta and sine theta forms a right triangle with the x-axis. You can only use Pythagorean theorem if the triangle have a right angle. We have now our first Pythagorean identities. Let's derive one of the main Pythagorean identities using quotient and reciprocal identities. Cotangent theta is equal to 1 over tan theta. Cosecant theta is equal to 1 over sine theta. Secant theta is equal to 1 over cosine theta. Okay, let's proceed to the next identity, which is the quotient identities. Tangent theta is equal to sine theta over cosine theta. Cotangent theta is equal to cosine theta over sine theta. Now we start with the primary Pythagorean identity, which is sine squared theta plus cosine squared theta is equal to 1. To derive one of the main Pythagorean identities, we will use the quotient and reciprocal identities. We divide the entire Pythagorean identity by cosine squared theta. Based on the quotient identities, tan theta is equal to sine theta over cosine theta. So let's simplify it. Cosine squared theta over cosine squared theta is simply 1. Based on our reciprocal identities, 1 over cosine theta is equal to secant theta. We can simplify it as secant theta. Why we squaring? The squaring happens because we are dealing with squared terms in the original identity. Dividing these terms transforms their square relationship accordingly, and this is our second derived identity. These derived identities are incredibly useful in various trigonometric applications. Now let's see an example of how we can use these identities in a real-world problem. A ladder is leaning against a wall. The ladder forms an angle with the ground. Given that the ladder is 10 meters long and the foot of the ladder is 8 meters away from the base of the wall, find the height at which the ladder touches the wall. So let's illustrate first. The foot of the ladder is 8 meters away from the base of the ground. And given that the ladder is 10 meters long, so we are asked to find the height at which the ladder touches the wall or the opposite side. Let's apply the Pythagorean theorem. The Pythagorean theorem states that the square of the hypotenuse is equal to the sum of the squares of the other two sides. Let h be the height at which the ladder touches the wall. Let be the base, and let's say the hypotenuse. We are going to simplify. H squared plus h squared is 64 and 10 squared is 100. Let's transpose or do the addition property of equality. Let's do the math. 100 minus 64 is 36. And now squared both sides to get the value of h. The square root of 36 is 6. So the value of h is 6. Let's verify our answer using the Pythagorean identities. Let's use first the sine squared theta plus cosine squared theta is equal to 1. I will first change the notation in order for you to understand. Our next step is to find the value of sine theta and cosine theta. We will use the SOHCAHTOA. We know that sine theta is equal to opposite over hypotenuse. Our theta is here, and the opposite of the hypotenuse is the right angle. The opposite of our theta is 6, and our hypotenuse is 10. 6 over 10 is simply 0.6, and that's the value of our sine. How about our cosine theta? Cosine theta is equal to adjacent over hypotenuse. The adjacent is 8 and the hypotenuse is 10. 8 over 10 is 0.8. Therefore, the value of our cosine theta is 0.8. Okay, substituting the value of sine theta and cosine theta. 0.6 squared is 0.36 and 0.8 squared is 0.64. If we add 0.36 and 0.64, it will give us 1. This confirms that our values for sine theta and cosine theta are correct. How about we verify our answer using the tan squared theta plus 1 is equal to secant squared theta. Let's change the notation first. We already know that tan theta is equal to sine theta over cosine theta. Let's substitute the value of cosine theta in sine theta. Tan theta is equal to 0.6 over 0.8. 0.6 over 0.8 is equal to 0.75. Our tan theta is 0.75. Let's solve for secant theta. Secant theta, if you can still remember, is equal to 1 over cosine theta. We already have the value of cosine theta, which is 0.8. 1 over 0.8 is equal to 1.25. Now we find the value of secant theta and the tangent theta. We are now going to simplify. 0.75 squared is 0.5625. 0.5625 plus 1 is equal to 1.5625. This confirms that our values for tan theta and secant theta are correct. By both the Pythagorean theorem and verifying with trigonometric identities, we have confirmed that the height of which the ladder touches the wall is indeed 6 meters. This calculation shows how trigonometry helps solve practical problems. Trigonometry isn't just for solving academic problems. It has vast applications in the real world. Architecture. Architects and builders use trigonometry to design buildings and structures. It helps them calculate angles, lengths, and heights to ensure everything is built correctly and safely. Navigation. Sailors and pilots use trigonometry to find their way. GPS systems use trigonometry to determine your exact location by measuring distances from satellites. Physics and engineering. Trigonometry helps in understanding waves, forces, and motions. Engineers use it to design machines, electrical circuits, and systems. Astronomy. Astronomers use trigonometry to measure distances to stars and planets and to study their movements. These examples highlight the importance of understanding trigonometry in various fields.
Okay, that's the end of the discussion. To summarize, today we derived two Pythagorean identities. We also saw how these formulas are applied in solving real-world problems, like finding the height of a wall. Understanding these concepts is crucial not only for academic success, but also for solving practical problems in various fields. I hope you found this tutorial helpful. If you enjoyed, please give a thumbs up and subscribe.